Welcome to the digital seminar series organized by the Statistics Assessment and Data Management Corps, a part of the HIV Center for Clinical and Behavioral Studies at the New York State Psychiatric Institute and Columbia University.
Hello, my name is Martina Pavlicova, and I'm a faculty in the Biostatistics Department in the Mailman School of Public Health. Today, I will talk about the purpose of pilot studies in modern research. The first part will be about why do we have pilot studies? Should we compute an effect size using pilot studies? And should we compute p-values in pilot studies? This part was done in collaboration with my colleagues Edward Nunes, Amy Campbell, Mei-Chun Hu, and Kale Basaraba. So I would like to start with a quote of Helena Kramer from her paper that was published in Archives of General Psychiatry already in 2006. Helena Kramer says, "Clinical researchers often propose pilot studies to determine whether a study is worth performing and to guide power calculations. The most likely outcomes are that studies worth performing are aborted, and studies that are not aborted are underpowered." So this is a problem that most likely can happen to all of us. And we will illustrate this problem on data from a large 10-site, 2-arm controlled clinical trial of a computer-delivered behavioral intervention for substance dependence. That trial had 507 subjects, and it was funded by NIDA under a Clinical Trials Network. So before we start, we need to discuss a little bit what is hypothesis testing and mention some definitions. Then we will play with our trial, and we will actually select a one site as a pilot study and see what effect size we would arrive and what kind of sample computation it would suggest for a future potential R01 study. So what was the study about? The study we will be using was a 2-arm randomized, 12-week-long controlled trial with 2 treatments. One was tau and the other was TRX. Tau was treatment as usual, and TRX was tau plus therapeutic educational system. Our primary hypothesis was that TRX will significantly increase the odds of abstinence at the last 4 weeks of the study compared to tau. The outcome then was abstinence from drug use or heavy drinking at the last 4 weeks of the trial. So our primary hypothesis then was tested by hypothesis test. In every hypothesis test, we have to set the null and the alternative hypothesis. The null hypothesis is the boring hypothesis. It's the hypothesis that nothing happens, that treatment is really not better than tau. So in this case, our null hypothesis is that the 2 treatments, tau and TRX, do not differ in abstinence rates during the last 4 weeks of the study. The alternative hypothesis is the one that we want to prove, and that says that the 2 treatments, tau and TRX, differ in abstinence rates during the last 4 weeks of the study. Notice that we don't say that TRX is better than tau, because all granting agencies require us to do a 2-sided hypothesis test. In other words, we have to consider the option that TRX will be significantly worse than tau. That is actually harder to prove. So our alternative hypothesis that we would like to show is that the 2 treatments, tau and TRX, differ in abstinence rates during the last 4 weeks of the study. So when we do the hypothesis test, we can actually arrive to 2 conclusions. One is that we don't reject null hypothesis, and the second conclusion is that we reject null hypothesis. If we don't reject null hypothesis, we technically didn't prove that tau and TRX differ. If we do reject null hypothesis, because null and alternative hypotheses are complements, we can actually accept the alternative hypothesis, and we can say that the data provide enough evidence that the two treatments, tau and TRX, significantly differ in abstinence rates during the last 4 weeks of the study. So these are two potential results of hypothesis tests. However, the reality can be different, and the reality has two options also. In reality, the TRX might not be better than tau, or the TRX might be truly better, different than tau. So in considering the reality and the results of hypothesis test, we have actually 4 potential options that can happen. In the upper left quadrant, we have the case that TRX is truly not better than tau, and at the same time, we did not reject null hypothesis. That is actually a correct conclusion. If TRX is not better than tau, then the correct conclusion is to not reject null hypothesis. It is correct, but it is not very exciting. What happens in the upper right quadrant? In the upper right quadrant, we have that the treatment is truly not better than tau, but we did reject null hypothesis. That is a wrong conclusion, and we call that type 1 error. Type 1 error is, in other words, that treatment is found erroneously superior. In the lower left quadrant, we also have a wrong conclusion. But in this case, the treatment is truly better, different, but we did not find it significant. So that is a type 2 error, and it is that the treatment is found erroneously not superior. Well, in the last 4th quadrant, this is the correct answer to the correct situation. If treatment is truly better, and we do reject null hypothesis, that means that the data provide also enough evidence that the treatment is significantly different than tau, we actually compute so-called power, and that is a probability that TRX is found correctly superior. As the researchers, we would like to be in the 4th quadrant. The chances of landing in the 4th quadrant we want as high as possible. So we always try to maximize the power because we want to maximize the chances, the potential that if our treatment is truly better than placebo, than tau, then we actually will have data that will correctly find the treatment superior. So what causes the errors? Well, the main cause of the errors is random sampling, and random sampling is never perfect. It can accidentally favor TRX when truly not superior. Maybe there are subjects that would get better regardless whether they are on TRX or tau, and they all stack up on TRX. So the TRX looks superior than tau, but actually is not. Or accidentally it can disadvantage TRX when truly superior. So maybe our treatment is truly better, but subjects who wouldn't do well regardless what they got, all got randomized to treatment and disadvantaged the treatment. So type 1 and type 2 error are because of randomness, because of the chance error, because of the random sampling. And data can favor erroneously TRX in case of type 1 error, or data can erroneously don't provide enough evidence that TRX is superior in case of type 2 error. However, in case of power, the data are aligned with the truth. They don't work against the truth, and data correctly provide enough evidence that TRX is superior. So our goal always, when planning a large randomized clinical trial, is to maximize the power. So how do we protect the study? In a best case, I would like to have both type 1 and type 2 errors as small as possible, and I would like to have the power as large as possible. So in a best case scenario, I would have type 1 and type 2 error to be 0% and power 100%. Unfortunately, that is not possible because type 1 and type 2 error are closely related in a seesaw relationship. As type 1 error increases, the type 2 error decreases. Or if we decrease type 1 error, the type 2 error will increase. If we decrease type 2 error, type 1 error will decrease. So what we do is we actually first take care of type 1 error. And we take care of type 1 error by pre-selecting level of significance alpha. Most commonly, we pre-select level of significance alpha to be 5%. And the hypothesis tests are done in such a way that they always guarantee that the probability of type 1 error will be at most equal to the pre-selected level of significance 5%. So by selecting level of significance 5%, I am basically bounding the chance of type 1 error happening. In other words, I'm saying there is at most 5% chance that if the TRX is not truly better than tau, we will find it significant. We will find it significant. But type 2 error and power are closely related. They are actually complements of each other. So if we, for instance, strive to have power of 80%, that means we bounding type 2 error to be 20%. Higher is the power, smaller is the type 2 error. Hence, if we, for instance, choose to have a power of 90%, our chance of type 2 error will be only 10%. Most of the granting agencies require us to have power of the large clinical trials of at least 80%. In other words, they allowing the chance that our treatment is truly significant, it's truly better than tau, but we will not find it significant to be up to 20%. If we select power 80%, we basically giving ourselves 20% chance that if our treatment is truly better than tau, we might have 20% chance to not find it significant just because of random chance. That is quite high. So really having as large power as possible is the best thing for our study. So what affects power? How can I affect power? There are two things that affect power. First, power depends on the expected effect size. Better the treatment is, better than placebo, larger the power will be. In other words, the more prominent the difference between effects of tau and TRX, the more likely the random sample shows the true superiority of TRX. That means the higher the power. But the power also depends on sample size. The larger the sample size, the more likely the randomness will average out, and the more likely the results will reflect the truth that TRX is superior to tau. So again, it will increase the power. So power is connected to both. The effect size, how much better the treatment TRX is better than tau, and the sample size. So when we're planning a large R01 study, we always have to think about how many subjects we need. And we usually compute how many subjects we need to have a study powered of at least 80%. But we also need to know what effect size we expect to observe. And that is the problem. How do we know what effect size we expect to observe? Many times people use pilot study to estimate the expected effect size. Should we do that? If we could estimate the effect size from a pilot study, we probably wouldn't need a large R01 trial. So let's support this argument by playing with our data. The data contain 507 subjects from 10 participating community treatment programs. We have 10 sites across the United States. All 10 sites performed the same protocol and they tested the same hypotheses. What we will do now, we will pretend that we are at the study of planning the research, and we can pick one site as our pilot study. So here we have the 10 sites, site 1 to site 10. Each site can actually randomize a different number of subjects. If we pick site 1, our pilot study will consist of 50 subjects. If we pick site 2, our pilot study will consist of 53 subjects. Site 3 is the largest site, so we actually will get 60 subjects. The smallest site, I believe, is maybe site 5, where we have only 48 subjects. So, which site do you wish to select as your pilot study site? We know that randomness is actually or can be averaged out. So larger our pilot study, the better. More likely we are to discover the truth. So we would probably pick the largest site possible. In this case, it is site 3. We will pretend to run the study within the selected site and analyze the data using logistic regression as we would otherwise to see whether the outcome of abstinence from drug use or heavy drinking at last 4 weeks is associated with random treatment assignments, and we will control for baseline drug abstinence and baseline stimulant use. So that is the analysis we would do. So pilot studies are typically small. Classic pilot studies have maybe 10 subjects, 12, 15, 20 subjects. In this case, we actually performing quite large pilot study. Our smallest site is 49 or 48, 38 actually, site 4, and our largest site is 60. So this would be a potentially quite large pilot study. We would assume that because we have such a large pilot study, the results will be pretty close to the truth, and we can rely on the effect size from our pilot study to inform a large R01 power computation. So we will start with site number 3 because it is the largest site, and then we will pick randomly several sites to see what will happen. So without any other information, we looked at the sample size. We selected site 3 because it has the largest available sample size, and we analyzed it. So our site 3 contained of 60 subjects. When we analyze, when those 60 subjects were treated with TRX and tau randomly, we obtained the results and we analyzed the logistic regression. We obtained the odds ratio of 2.51. It means that the odds of being abstinent in the last 4 weeks of the study were 2.51 times higher on TRX than on tau. That is quite high. The 95% confidence interval, however, is from 0.67 to 9.33. The 95% confidence interval is quite wide because it reflects the small sample size. 60 subjects is not that many subjects to analyze and to know the truth. So the 95% confidence interval tells us that the true population odds ratio of TRX compared to tau could be 0.67, which would suggest that TRX is almost significantly worse than tau, up to 9.3, which would suggest that TRX is really much better than tau. So almost all possibilities are included in the 95% confidence interval. When we tested this odds ratio for significance, the p-value was 0.18. So even though we obtained quite optimistic odds ratio of 2.51, it wasn't significant. Now, the big part. Why did we do that? We did that because we wanted to know what the potential effect size will be in a large R01. So if we make the assumption that large R01 will behave the same way as site 3. In other words, if we use the odds ratio of 2.51 to inform power computation for large R01, it would suggest that in large R01 we should have at least 160 subjects. But site 2 was maybe similar in size, so maybe someone would suggest that maybe we shouldn't look at site 3, someone wants to use site 2. So now my hope is that because my sites are quite large, that site 2 will not have that drastic different results, that site 2 will not have very drastically different results than site 3. That basically the estimates of odds ratio from site 3 and site 2 will be close to each other and close to the truth. So what happened if I analyze site 2 separately? In site 2 we had 53 subjects, a little bit less than 60. And when those 53 subjects were randomized to treatment and placebo, TRX and tau, and their results were analyzed, we obtained an odds ratio twice as big as in site 3. The odds ratio was 5.41. That is much larger odds ratio than before. Still very optimistic, but the 95% confidence interval is still going from negative side 0.62 up to a very strong positive side 47.14. And that is because a smaller sample size. The p-value is still not significant, is 0.13. And if we actually use the odds ratio of 5.41, which is a very large odds ratio, and if we use that to inform a power computation in large R01 clinical trial, for a large R01 clinical trial, we would suggest that we should have only 58 subjects in large R01. That wouldn't be very large R01. What would probably happen? The 5.41 is probably too large. And we shouldn't expect to have or to observe the same odds ratio again in large R01. So in large R01, probably the odds ratio that we would observe would be much smaller, but then 58 subjects would not be enough to find that smaller odds ratio significant. And we would end up with unsuccessful large clinical trial. So let's look at another site. We chose site number 7 just because 7 is a nice number. And in site number 7, we had 50 subjects. And the odds ratio that we received from subjects from site 7 was 1.43. That is very small. If we use the odds ratio of 1.43 to inform power computation for large RCT, we would require to have at least 994 subjects in the large RCT. And that would be unfeasible, and probably we would not perform the large trial. Last but not least, we picked site number 4 because it was the smallest site, and we just wanted to know what can happen if we pick the smallest site offered. So the smallest site contained only 38 subjects, and when we analyzed it, we actually obtained the largest odds ratio. The 38 subjects stacked up so well that all the well-performing subjects were in TRX and all the badly performing subjects were in tau. So we obtained an odds ratio of 7.15. It still wasn't significant, but if we assume that we will again observe the same odds ratio in a large RCT, we would need only 46 subjects in the large RCT. That wouldn't be very large. And this assumption that we will again see the same odds ratio in large RCT is very brave. It's most likely not going to happen. So here are all the sites. All 10 sites, the bolded ones are the ones that we actually went through, but you can see the rest of them. When you quickly look at the p-values, you can see that all the results, each site did not lead to significant results. All sites led to insignificant results. The odds ratios varied drastically. The smallest odds ratio that we observed was in a site 5, 1.22, and the largest odds ratio that we observed was actually in a site 4, and that was 7.15. There was a wide spread in the odds ratio, in the odds ratios. However, when we analyze all 10 sites together as one large RCT, all 507 subjects together, the resulting pooled odds ratio was 2.18, and it was significant. So in conclusion, our large randomized clinical trials actually was significant, and TRX was significantly better than tau, but only when we combine all 10 sites together. When we looked at each site separately, we got very variable results with a lot of spread among the odds ratios, and none of them was significant. If we just pick one site as our pilot study, how would we know whether we are having results that are too good to be true or maybe too bad and the truth is actually much better? It's very hard to tell. So here is a picture of a scatter plot of, on an x-axis we have site sample size, and on a y-axis we have the obtained odds ratios, and you can see that they are basically scattered all around. The odds ratio from a full pooled study from all 507 subjects is actually right here, slightly more than 2. So a couple of sites were close, but most of the sites produced a site-specific odds ratio really far away from the true odds ratio because of just random chance. So when I presented the results to my colleagues, they actually suggested that the variation between sites is because of the site differences. They said, well, sites are different. They are in a different location. They serve slightly different subjects. They also work slightly differently because the human factor within sites. And that it should be eliminated and the results should be better if I just randomly select subjects across all sites. So I said, okay. So what we did next is we randomly selected 60 subjects from all 507 subjects. 60 is still a very large number for a pilot study, so we should be okay. And we run the same analysis. We would expect that the 60 subjects is large enough sample to result in sort of a stable odds ratio. So if we repeat the process again, our new odds ratio should not be that different than the old odds ratio. So we should not see much variation in the repeating the process. So let's see what happened. We did that once, twice, 3 times, and then we did that 1,000 times. So our sample number 1, we just went in, randomly selected 60 subjects out of all 507 available subjects. We analyzed them between treatment and placebo, and our sample odds ratio for that particular random sample of 60 subjects was 4. So I actually plotted on a very simple histogram, and you can see the blue bar at 4 because we just did it once. The question is, if we repeat the process, I put my 60 subjects back into the pool of 507, and I randomly select a new 60 subjects. Maybe some subjects will repeat in the new sample, and maybe not. There will be some new subjects. So I don't expect the second sample of 60 subjects having exactly the same odds ratio as the first sample of 60 subjects. But because I'm using random process and maybe I hope that these two odds ratios will be very close to each other. So what happened? The second odds ratio was 10.5. So you can see on my very simplistic plot that 4 and 10.5 are quite far from each other. So these two random samples of 60 subjects, that is pretty high, from 507 already are producing quite different odds ratios. So we did it the third time. And the third time when we selected 60 subjects again from 507, we obtained an odds ratio of 0.5. In the third sample of 60 subjects, the treatment was actually worse than tau because the random chance. We accidentally picked subjects who didn't perform very well on treatment, and we accidentally picked subjects who did really well on tau. So the treatment, because of random chance, was disadvantaged. So 3 random samples led to 3 very different conclusions. If I performed just one of them as my pilot study, I wouldn't know where is the truth. So just to repeat the process more and more times, we did that 1,000 times, and we created a little simulation where you can see every single time we simulate another 60 subjects and we analyze them, a little new bar, blue bar appears. So let's watch the right side of the screen as the simulation is performed. So here we see the first simulation, sample 3 is around, or the first simulation is 1, but that's because we simulated again. And let's see what happens. And you can see that as we repeat the process many, many times, most of the odds ratios are somewhere between, 1 and 3. That's where the blue bars are the highest. But once in a while, the odds ratio is very close to 0, saying that treatment is really worse than tau. And once in a while, the odds ratios are up to 18, 19, are very, very large, suggesting that treatment is very much better than tau. So these are the results of 1,000 simulations. These are 1,000 sample sizes, 1,000 little pilot studies, and the results can be drastically different. 60 subjects in a pilot study will not produce stable odds ratio. These odds ratios have very wide spread. So if we relied on one pilot study to inform us what is the effect size, what is the odds ratio, we wouldn't know where we are, how likely we are to be really far from the truth. If the truth is 2.5 or 2.1, we are really far, many samples are really far away from the truth. So I showed that to my colleagues, and my colleagues suggested that maybe it is because I just randomly pick 60 subjects and don't care about anything else. That maybe I should somehow portray the situation, the true reality better, and that I should stratify for sites. That I should control that each site is represented in my sample of 60 subjects. So what we did is we selected 6 random subjects from each of the 10 sites. That together is again 60 subjects. So in this case, we know that every time we select a stratified sample of 60 subjects, all 10 sites will be represented. So we will get really sort of a mini-me of the whole study. And the hope was that by stratification, we will actually produce much more reliable estimate of odds ratio, that the variance, the spread of all those odds ratios will be much smaller, and we could trust it. So what will happen? We did that, and in our first stratified sample, where we have 60 subjects, 6 from each site, the first odds ratio was actually 13.5. We already know that this is too large for the study. And I plotted, and here we are. That is the first bar at 13.5. And so I said, okay, maybe the second one will be near that, and we will have some stable results. So we randomly selected another 60 subjects. We placed the first 60 subjects back into the pool, and we randomly selected new 60 subjects, 6 from each site. Will the second odds ratio be different than the first odds ratio? Well, the second odds ratio for the second sample was actually 0.5. 13.5 and 0.5 are very, very different. So the hope that we will obtain much more stable odds ratios by using stratified sampling process is probably gone. When we did that the third time, the odds ratio was somewhere in the middle of 5.5. So we can see already on 3 samples that the random sampling process is not miraculous. It will help to even out the treatment and placebo group, but yet there are still differences. And the random chance, we don't know what will happen. If random chance will accidentally favor the treatment or accidentally favor the tau. So we repeat that 1,000 times, and now let's look what happens in the 1,000 times simulations. So 1,000 times we selected a stratified sample of 60 subjects, and again you can see that most of those samples are somewhere near between 1 and 3 maybe, but a lot of those samples are actually quite smaller than 1, close to 0, and a lot of those samples produce odds ratio that is too high, maybe larger than 10, 12. There are some odds ratios that are close to 17 or 19. That is really, really large. How much faith do I have in those odds ratios? Well, not much. This is just all based on random chance. So here are the 2 simulation results. And regardless whether I just randomly selected 60 subjects from the 507 or whether we use more sophisticated stratified sampling, the results are very similar. They show that the variation from sample to sample in the odds ratios is very high, and that we actually cannot guarantee to obtain stable results from 60 subjects as a pilot study. So let's look at the results again. Here we have the 10 sites. Regardless which site I would select, my study, my large RCT would be badly informed. In case of site 1, if I selected site 1 as my pilot study, I would probably never perform the large RCT because my pilot study suggests that I need 2,210 subjects in the large RCT. Site 5 suggests even 3,188 subjects. That's too large. But if I selected another site like site 2, site 3, site 4, they would actually suggest to have much smaller sample size than I needed, and my large RCT would be probably underpowered. Because the expectation would be that the same odds ratio as I observed, for instance, in site 2, 5.41, would repeat in a large RCT. But what are the chances of that? The chances are very small. So let's go back to what Helena Kramer said. Helena Kramer said, clinical researchers often propose pilot studies to determine whether a study is worth performing and to guide power calculations. In that case, the most likely outcomes are that studies worth performing are aborted because the pilot study ended in a small effect size accidentally, or studies that are not aborted are underpowered because the pilot study accidentally ended in a large effect size, which resulted in a small sample size for the RCT, which resulted in underpowered study. So what are the conclusions? Our conclusions are that all pilot studies failed to detect TRX significantly. They failed to detect that TRX is significantly better than tau. The p-values is higher than 5% across all sites. The second thing that we saw is that if we rely blindly on the site as a pilot study, their point estimate odds ratio from the site, we will either grossly underpower the proposed RCT, or we will need unfeasibly large sample size for the RCT. Both are not great results. So, what should we do? The large RCT should be powered to detect as significant the smallest effect size that is clinically meaningful in the context of the target disorder. Large RCT should not be powered based on the point estimate from a pilot study, because as we saw in the simulations, the odds ratios from pilot studies are very unreliable. They have very wide spread. Instead of it, we should look what is our treatment and what is our placebo, what is our tau, and how well we would like the treatment to perform. In a very simple example, if treatment as usual for flu basically results that subjects gets better from a flu in 7 days, then what would we want our new treatment to be? What would be the smallest possible clinically meaningful effect size? Would it be clinically meaningful if our new treatment shortened the time of flu from 7 days to 6 3/4 by just quarter of a day? That maybe is not clinically meaningful. But if our new treatment can shorten the duration of flu from 7 days to 6 days, that's a 1 working day. That's a 1 day less of a flu. That is maybe a clinically meaningful effect size. So we should power the study, the large RCT, to find the 1 day improvement decrease in a flu duration as significant. This is how we should compute the power for a large RCT. So why do we have pilot studies? Should we abandon pilot studies if we cannot compute effect size from pilot studies, if it makes no sense to compute effect size from pilot studies? Well, pilot studies' purpose is very limited, but they are extremely valuable. Not in computing effect sizes and p-values though. We should use pilot studies to actually demonstrate feasibility, acceptability, safety, and tolerability. The success of future clinical trials should not be based only on the effect size estimated from a single pilot study, because we know that is very unreliable, but rather on confluence of data and opinions from biological, preclinical, and clinical levels of evidence, supporting the likelihood of a clinically meaningful effect. All experts should sit together and think about what is the clinically meaningful effect. How much better the TRX needs to be than tau for us to care. And then that's what we power for, not use the effect size from pilot study. So let's talk a little bit more about what are pilot study for. And I will base this part on 2 papers, one by Leon from 2011, published in Journal of Psychiatric Research, and the other is on Helena Kramer paper from 2006 that we have already talked about. Basically, we would like to know, why should pilot studies be an essential part of research? And still, what about the effect size and power? So pilot studies are essential. We cannot perform a proper RCT without running a pilot study first. But pilot studies are here to demonstrate the 4 magic properties, and that is feasibility of our treatment, acceptability of the treatment versus placebo or tau, safety, and tolerability. We need pilot studies to make sure that our treatment is feasible, that our treatment is acceptable to subjects, to those who perform it, that our treatment is safe and tolerable. We want to use the pilot studies to fine-tune the protocol for RCT, that we will not encounter any problems with feasibility, acceptability, safety, and tolerability when we perform the large RCT. That is why we have pilot studies. So what could be feasibility? This is from the paper of Leon from 2011. He says that the aspects of feasibility can be examined in pilot study, like we can examine screening, where screening can be operated or quantified as number of screen per month. We can actually measure recruitment, number enrolled per month, or proportion of those who were screened and became enrolled. We can look at randomization. We can look at proportion of screen eligible who enroll, who were randomized. Do we have large proportion who actually were eligible and did randomize? Or do we have a lot of eligible subjects but not many end up randomized? Where is the barrier? How can we improve or remove the barrier? We should look at retention. Are the subjects staying in the study? Are they dropping out? Reasons why are they dropping out? Can we actually change the protocol to eliminate or minimize the dropouts from the study? Can we entice the subjects to stay in the study to the end? That is very important then for large RCT. What is the treatment adherence? Are our subjects adhering to treatment? Are they adhering to placebo? Or are they sort of not taking our treatment seriously? How can we improve adherence? Treatment fidelity. Assessment process. How many ratings which we plan we actually did? Could we do all the ratings? Many times we have the idea that we want to ask subjects so many different questions, we want to measure so many different scales, that it's actually unfeasible for subjects to sit there and answer 5 hours of questionnaires. So how many of those ratings are completed? How long the assessment visit takes? Is the length of the assessment visit actually a problem for treatment adherence? Or is it a problem for retention? Do subjects drop out when the assessment visits become too long? So feasibility can be assessed in treatment group, but also in a control group. It is important to have treatment and control group in the pilot study because we can better assess recruitment, randomization, blinding. That is very important. Is the blinding in the effect? Maybe in our pilot study, we should keep asking subjects to guess whether they are on treatment and placebo and analyze whether the guesses are still random or whether the subjects mostly guess right. Because if the subjects can mostly guess right what they are on, our blinding is not in the effect. The same thing about evaluators. If we want our evaluators to be blinded, we should ask them about their guesses, which subject is in treatment and which subject is in placebo arm, and see whether their guesses are still at random or whether their guess is becoming more and more correct as the treatment progresses. Tolerability is another essential part of pilot studies. Here is what Helena Kramer or Leon says in their paper. If some safety concerns are detected in pilot study, group-specific rates with their 95% confidence intervals should be reported for adverse events, treatment-emergent adverse events, and serious adverse events. When event rates are reported and actually no adverse events is observed for a particular category, then when we compute 95% confidence interval, the rule of 3 should be applied to estimate the upper bound of the 95% confidence interval. And the rule of 3 is that the upper bound is approximately 3 over n. So what does that mean? Here is an example. We have a pilot study of 30 subjects. And we are concerned about a specific side effect, but none was observed. None of our 30 subjects actually experienced the specific side effect. So we'll say the proportion of that specific side effect was 0. But what is its 95% confidence interval? And we should estimate the 95% confidence interval to be from 0, because we didn't observe any, up to 3 divided by n, 3 divided by 30. And 3 divided by 30 is actually 0.1, which is 10%. So in other words, even though we didn't observe any side effect in our study, that specific side effect, no occurrences, the 95% confidence interval says that in a large RCT we might observe between 0 to 10%, just because we had only 30 subjects. And it is something to consider for future. So what about effect size and power? Well, pilot study cannot influence power computation for large RCT by suggesting an effect size, because pilot studies are unreliable. As we saw in our simulations, pilot studies can end up with a very small effect size just by random chance, or with very large effect size just by random chance. If we could estimate the effect size from pilot study, why would we do RCT? We wouldn't need to do a large RCT. Pilot studies are very imprecise and can easily lead to either falsely positive results, which is type 1 error, when the odds ratio was too large to be true, or falsely negative results. That's the type 2 error, and those were the odds ratios that were close to 0, even though we knew the treatment is actually effective. We should actually look at the 95% confidence interval and look at the width of the 95% interval and look at the effect sizes from a lower and upper bounds, and to explore them for feasibility. But to estimate power and sample size for a large RCT, we should always use what experts consider clinically meaningful effect size. That is the most important part. The consequences of using pilot study effect size is that if pilot study results in falsely large effect size, type 1 error, the subsequent large RCT will be designed with less than adequate sample size. We will basically say you don't need that many subjects in a large RCT, because we expect that the observed odds ratio will be super large, but that will not happen, and we will end up with underpowered study. If a pilot study results in falsely small effect size, very close to 0, that's a type 2 error, then there will be no large RCT, because our power computation will say that we need thousands and thousands of subjects, and that is not feasible. The proposed study would be too large to be feasible. So again, properly designed randomized clinical trials should be powered to find significant clinically meaningful effect size or clinically meaningful difference. Should be not less, that would result in not very helpful treatment, or should be not more, because RCT would be successful only if the treatment was super good, much, much better than placebo, in other words, would have miraculous properties. So in conclusion, based on the Leon article, I would like to quote that the primary role of a pilot study is to examine the feasibility of a research endeavor. For instance, feasibility of recruitment, randomization, intervention implementation, blinded assessment procedures, and retention can be all examined. Investigators should be forthright in stating these objectives of a pilot study and bravely accept the limitations of pilot study. Grant reviewers should expect no more. Pilot studies are a necessary first step in exploring novel interventions and novel applications of interventions, whether in a new patient population or with a novel delivery system. Pilot results inform feasibility, which in turn is instructive in that it points to modifications needed in the planning and design of a larger efficacy trial. Nowadays, the primary aim of pilot studies should be exploring feasibility, tolerability, acceptability, and safety. We should measure those 4 magic properties, and we should make sure that the study protocol is fine-tuned based on the results from pilot study. But we should not use an effect size, or we shouldn't even compute an effect size in order to inform power computation for large RCT. So thank you for your attention.